Hi, everyone. This is Aaron Larson, Executive Editor of Power Magazine, and you're listening to the Power Podcast. On today's episode, I'm joined by Tom Nugent. He is the co-founder and Chief Technical Officer of PowerLight Technologies. So, Tom, thank you very much for joining me, and please tell a little bit about your company and what you guys do.
Hi, Aaron. Thank you very much for having me on. PowerLight Technologies used to be under the name Laser Motive, and people may have heard that a number of years ago. And we have been developing long-range optical power beaming technology. And this is a way to take energy from somewhere where it's easy to generate or access, whether that's a generator or an electrical outlet. And we convert that electricity into light and then project it either through the air or through optical fibers to some remote location where it may be very difficult to get power to. And then that light is converted back into electricity using specialized solar cells. And then the electricity can be used to power devices, charge batteries, or anything else that you'd want an extension cord. Because what this really is a wireless extension cord.
It sounds like science fiction to me. And it's really amazing that you guys are actually doing this. When you think about the distances, how far or how long is this extension cord?
Yeah, and you're right. We like to say that we're bringing science fiction to reality, and there are a number of different technologies that do what they call wireless power, but they all have different limits to their range. Some of them you're familiar with these induction pads that you can put your phone on, and those work over very, very short distances. One of the advantages that using near infrared light, as we do, is that it allows you to go very long distances, kilometers or even more. And the company got started a little more than a decade ago, winning a NASA technology competition, and has spent the time since then refining the technology, making it robust and efficient and safe, and understanding the markets and use cases. And we are now getting close to having products that we'll be releasing. And that really is, I think important to convey, because like you said, it's something that many people haven't heard of or don't realize where the technology is. And it's actually much, much closer to reality than a lot of people may have thought.
Yeah, I know I've seen the ways that you can charge your phone by setting it on a pad, and I'm still, I guess, kind of old school. I feel like I can't possibly charge my phone without plugging something into it, but I guess that's not true anymore. It's not the case. I need to move up my technology knowledge and start using these tools that are so innovative. How much power can be transmitted in this way? Are we talking just small amounts of power, or at some point in time, do you envision this being a replacement for the common transmission and distribution lines that we see today?
We have delivered as much as a kilowatt of continual power in some previous demonstrations, and we've delivered power at distances of 1 kilometer in the past as well. And we are looking to expand that. And there's different classes of devices that require sort of different power levels or different distances. You talk about your phone. Phones need maybe a few watts of power, and the distance is usually within a room, a few meters. Mm-hmm. There are a lot of use cases in telecom and other large industries that have devices that might need hundreds of watts, or in some cases, kilowatts of power. And the distances they need might be in that range of, say, 0.5 kilometer to maybe 2 or 3 kilometers. And in the future, you could envision different scenarios where you may need to deliver power for things like a remote military base or a small island where you might need to get tens of kilowatts or even megawatts, and you may need to go tens or hundreds of kilometers. And there are ways to that in the future. Right now, we're focused on that roughly kilowatt class of power over the kilometer scale distances. And there are these different applications in telecom, construction, the military, of course, and other areas like that have this need for powering communication nodes or sensors, security sensors, and devices like that.
You said we're very close to potentially putting these into service. What sort of challenges do you have left to overcome before you can really roll this out on a grand scale?
There's been a number. It's been interesting developing this technology because, on one sense, what we are trying to ultimately make is something that will be very simple. It's a wireless extension cord, and just as you go down to the store and buy an extension cord, you don't need a manual on how to use it. You just plug it in and it works. And so we've been trying to make this technology that simple to use. But it really is a system of systems with all these lasers and photovoltaic cells and beam tracking. And one other part of that is safety. One of the big innovations that we have brought to reality and are continuing to improve is a safety system that acts sort of like the insulation around your extension cord. When you plug a wire in, it's a 120 volts, and that can be dangerous. But with things like the insulation around the copper wires and your GFI circuits, it can be safe for people to use that. And we've been doing the same thing for optical power, making it so that if anything tries to approach the high intensity light, the laser will temporarily shut off while, say, a bird might fly through where the beam would have been. And then it'll turn back on after that beam path is clear. And so we can do this because at the receiving end, there's usually some amount of energy storage, often in the form of a battery. And so that battery can sort of keep providing the power to whatever device is being powered while the beam shuts off temporarily. So we've done a lot on safety, and there's more to do to work through making it as robust as we want it to be able to be sold in a product. And then the other challenges are more in the sort of the packaging, making the system really fully weatherproof for years at a time, and being able to make it more compact and easy to use. But all of the fundamental technology in terms of the lasers, the photovoltaics for converting, a lot of the sort of secret sauce that we add to make all these efficient, doing the tracking of the beam to keep it centered on the receiver. All of the fundamental parts of that have really already happened. And so we're in this really exciting phase, and the sort of challenging phase of making it be something that can be robust and reliable to operate out in the field in various weather conditions for years at a time.
And you've kind of talked about the technology. So you're basically converting the power to light and then reconverting it back at the other end using a solar cell of some sort from light back into power. Mm-hmm. Am I explaining that right?
That is correct. That's exactly right.
Okay. That's an interesting way to get power from one point to another. Very interesting. Are there advances that you see in the future where lasers and efficiencies would improve? Is that where you're going to get those longer distances where you can perhaps go hundreds of kilometers and so forth?
Yeah, there's a couple of things in there. So one, and part of what enabled us to start in the first place and see an opportunity is that lasers have been, for the last few decades, on this steady sort of Moore's Law-like improvement of getting more efficient, getting higher power, and getting lower costs. And the cost of these high-power lasers falls in half roughly every 3 years. And so there's more to do to continue making those efficient, but there are lasers available today that are over 60% efficient. And similarly, on the photovoltaic side, the solar cells, because we are using one wavelength of light, we can match those solar cells to the wavelength from the laser. And there are these specialized solar cells for laser conversion that are more than 60% efficient today. And so that efficiency is, end to end is already much, much higher than it was when people first started looking at this, many decades ago. And there are a lot of researchers around the world in universities and government labs continuing to work to improve the efficiency of those components. And that increased efficiency makes the system design easier and helps reduce the costs. To go to the longer distances, one of the limiting factors for beamed power is that it is generally line of sight. That if there's a mountain in the way, you can't go through that. And similarly, if there's very thick clouds, you can't generally go through those. And so the atmosphere is the limiting factor generally in distance. But there are ways to relay, say if you have a high altitude system to redirect the beam down to other distances. And of course, there's been ideas going back, 60 years now, for collecting solar power in space and beaming it down to Earth. And a lot of that has focused on using microwaves instead of lasers. But there are pluses and minuses to each of those systems, which use sort of different parts of the electromagnetic spectrum. And so there are a lot of different options depending on where you are generating that energy in the first place, whether it's here on the ground or out in space, to then be able to send it over longer distances to get the power to where you need it.
So you kind of mentioned that you can't put these, it won't transmit through clouds. So using that space example, you'd have to find clear spaces where you can get the light waves through. Is that true?
That's true, yes. And that's where having batteries again comes in handy, because there are certain parts of the globe which may have a lot of consistent cloud cover, but large fractions of the Earth just have intermittent cloud cover. And so if the clouds come through for half a day or a day, you may have enough battery power to last you for that time if you're at some remote base, for example. But then once those clear up, you can go back to providing power and charging those batteries at the same time.
Now, when I think of a laser, I think of a pretty condensed piece of light where you don't need a big receiver. Would the PV cell be just a real small, like size of your watch type PV cell, or how would that work?
That's a good question. And you're right. A lot of people think of laser as a pencil beam. For our purposes, the beam is generally much bigger than that. It might be 15 or 30 centimeters across, so half a foot or a foot diameter, or potentially even bigger. And the photovoltaic cells we use are optimized for relatively high intensity light. And as I mentioned, they're higher efficiency than regular solar cells, because solar cells have to convert a lot of different wavelengths at once, and so they're less efficient. And so the receiver, depending on how much power, we can, deliver more than a watt per square centimeter. So something that's, say, a foot in diameter, you might be able to get, 2/3 of a kilowatt out of that. You might be able to get a horsepower's worth of electricity out of a receiver that's roughly 1 foot in diameter, 30 centimeters in diameter. And so it can be much more compact for the same amount of power as compared to solar cells, with the added advantage that it doesn't go off at night. But the intensity of that beam is not nearly as small as people think, and it's not nearly the intensity that might be used when people think of like laser weapons. So we're sort of in a middle regime between sunlight on one end being what we would think of as relatively low intensity. We're sort of higher than that, but also much lower than what people think of as say, laser weapons and the intensity needed there.
But as you had kind of alluded to earlier, if a bird flies through that beam, it's going to get basically electrocuted?
No, the general hazard with the near-infrared light that we use is that your eye can focus it, and so it can do eye damage from heating. Okay. And so that's where our safety system comes in, that it turns the laser off before anyone can be exposed to that. And so even in the worst case, the damage is sort of heating damage. It's not a lethality hazard. Your high voltage power lines, if you somehow get exposed to those, those can kill you. The lasers certainly can't do that. They're much safer than that. And we make them completely safe by just shutting it off before anything can get into that beam. And in fact, in some of the prototypes we've been developing and testing outdoors, we've even had cases where birds are flying through and the laser shuts off before they can get into that power beam, and they are just perfectly safe.
I guess when I think of a bird flying through, they wouldn't necessarily be looking directly at the beam either, would they? So maybe they wouldn't even get hurt at all. Is that true?
That's completely true. And you're right. And in a lot of cases where you get exactly that situation where people wouldn't be looking into the beam, and so they probably wouldn't get hurt anyway. But to be safe, you turn it off anyway because you don't know.
Yeah.
And there's a lot of work we're doing right now on exploring sort of the edge cases of what are sort of the weird cases, or if someone's being malicious, what would someone do to try and cause harm, and how do we make sure we protect against those? And so you're right. We are trying to be safer than you might otherwise think. That the bird's probably not going to be looking this way. We don't want to sort of rely on luck to be safe. We want to have that safety engineered in.
Now, another thing that I was thinking is, to get longer distances, you could go from one short distance and beam it again, but I assume there's some losses along the way, so that wouldn't really be an efficient way to move the power further down the line. Is that true?
That's exactly right. That if you're sort of converting the light back into electricity and then reconverting it back into light, every time you do that, you have those losses. And that's why redirecting the beam with a mirror of some kind is more appealing, because then you don't have those losses.
Okay. So when you think about other devices and ways that this could be used efficiently, profitably, cleanly, what do you see in the future? What are some places that you really think this could be a game changer?
The areas we're focusing on right now are places where it's either too expensive, impractical, or slow to run a power line. If you can run a power line, you should, because it can always be more efficient. But there's cases, for example, with the small electric drones, these aircraft, where you, in most cases, can't run an extension cord up into the sky, certainly not over any reasonable distance. Another are situations where you want to rapidly get power to some place. For example, remote telecom cell towers, or sensors if you are putting in a new installation, where you could run a power line, but if you're dependent on the local utility, there's permitting and other issues that cause that to take months. So I've even heard cases of years to wait for a power line to be installed. And so situations where you really want to get that power deployed very quickly is another type of situation that this can benefit. And related to that, there may be cases where it can be very expensive to run power, especially if you're in, say, an urban center where there's already installed power and everything. It can be expensive to go through and then try and add more lines in certain situations. So it may also be a cost savings in some cases to be able to quickly do this and not have to go through the potentially involved situation of trying to run new power lines in very congested areas.
You had mentioned earlier talking about fiber optics and using that to transmit the power. What are the specific advantages of doing that over running, for example, a wired connection? Because basically you have to do pretty much the same thing to do fiber optics as you would with a power line, right?
That's true. And there are a couple cases where the fiber can make sense. There are more and more installations, whether it's a Wi-Fi repeater or a cell repeater, that has fiber going to it for data. And in construction, you sort of have two different people run the fiber versus running the electricity, or so I've been told. And there's different hazards and permitting if you're running a power line. If you just have one fiber bundle that has both the data and the power to it, that can be simpler and cheaper for installation. But there's also cases where you need to go into high voltage environments. For example, there are sensors that utilities place on high voltage transmission lines, and you want to electrically isolate those sensors And so the optical fiber is not conductive. And so you can provide, again, power and data to sensors where you don't want an electrical connection into that high voltage environment. And the last one is for underwater vehicles, where some of them operate completely autonomously, but there are also ones that use optical fiber for data, but they frequently don't use electrical wires because underwater the copper is both relatively dense, and that causes you to put a negatively buoyant material around it to have the overall cable be neutrally buoyant. And to go these distances, they have to go to high voltage. And underwater, that also requires a lot of protection against galvanic action and shorting. And so what it winds up is that if they put copper wires to these underwater vehicles, the thick cables, because of all this insulation and negative buoyancy material, winds up causing too much drag and problems on those vehicles. And so for ones where they're already using a thin fiber optic cable just for data, and then the vehicle currently has an onboard battery, doing the power over fiber will allow you to maintain that thin cable connection, but get much longer operation time because you're not reliant on just what's stored in the battery.
And you mentioned, that some of these applications are with the Department of Defense. I assume maybe the Department of Energy. Are they doing any research or helping with any funding on different projects to make this kind of a faster process to get to commerciality?
Yeah, the Department of Defense has been a wonderful supporter, and we really appreciate everything that they have done, and they see the potential dual use for this technology for a lot of the different applications I've mentioned, and so there's some great overlap there, and they've been great supporters and interested in developing this technology, this end of the microwave technology. Recently, the Department of Energy has they had a video from one of their researchers about optical beam to power, and there's starting to be some interest there. And so we're hoping to be able to work with the Department of Energy too. And we think part of the value of this from the perspective of the Department of Energy is that we are taking the electric grid and extending it to areas where it currently doesn't reach, whether that's into the air or out at the edges of the grid into places where it currently doesn't reach. And so those are the two organizations. We've done a lot of work with the DoD, and we're hoping to do some with the DOE soon.
Are there any power companies that have come to you, any utilities that are interested in this technology and working with you to collaborate on uses?
We're not currently working with any utilities. The high voltage power line application I mentioned is one example where some of the very low power, short distance power over fiber is currently being deployed by some other companies. And we've had some discussions in the past with some utilities, and I think as we get our products available, I expect that there will be more interest for some of these related applications for them for monitoring of their networks, for example.
All right. Well, you've answered most of my questions. Is there any last words you'd like to leave the audience with?
Pretty much just what I started it with, which is that the technology is really closer to reality than people might realize. There are some very tiny, very low power examples of what I've discussed that are already out there. But we are looking to have these sort of higher power kilowatt-class devices at kilometer-scale distances out for early customer testing and use in the next couple of years.
All right. Well, thanks a lot, Tom. This has been really interesting. I've learned a lot about the possibilities that are on the horizon. So thank you for your time and thank you for speaking with me.
Thank you, Aaron. It was my pleasure.